Welcome back to part 2 of Pre-Calc Notes 1.7 or Trig P.8. We last talked about taking parent functions, so maybe an x squared and x to the third and square root of x, and we dealt with shifting these graphs, so moving the x and y intercept. And now what we're going to be doing, instead of talking about shifting, is we're going to be talking about transformations of graphs. So these are distortions and not shifts. Instead of moving the graph around on the x and y axis, what we're going to be doing is we're either going to be expanding it or shrinking it, based upon what type of numbers that we add into our problems and where we add them in. So if I want you to look at the parent function, again, I'd like you to have three different colors with you in terms of, maybe a pen, a pencil, and a highlighter, or maybe specifically 3 highlighters. If you have the absolute value of x, and that's what this red graph is here, that's our parent function. What we're going to do to get to the pink graph, which is 3 times the absolute value of x, is we're going to multiply the parent function by 3. To get to the blue graph, that's 1/3 the absolute value of x, we're just going to multiply the parent function by 1/3. And notice what happens is when I multiply it by a 3, it made the graph much skinnier. So this was skinnier. Whereas when I multiplied it by 1/3, it made my graph much fatter. Notice that this blue graph is opening much wider than this red graph does. So this is going to make it be a fatter graph, or wider is probably a better way of saying that, a wider graph. So depending on the number that we multiply our parent function by, that will either stretch or shrink our graph. Okay, so we need to use that verbiage here. A vertical stretch is when it is being expanded rapidly along the or the y-axis. So it's vertically, if I was to take and pull on the ends of these red lines and I was to pull them vertically, it would make this. So I would stretch it much more vertical. So that is the same as a stretch. On the other hand, and that's for the pink graph, on the other hand, if you were to be able to put your hands on both ends of these, the red V here, and push down on it, it's going to make the V open up much wider, and that's called a vertical shrink. And so when you have a number that is between, we call this A, if your A value is greater than 1, you're going to make a skinnier graph, or stretch it. If your A value is between 0 and 1, that's when it's going to be a wider graph and a shrink. And just to add one more in there, if we're talking about negative a's, in this case we're talking about numbers that are positive, less than 1, basically from 0 to 1, or bigger than 1. If it's negative, all the negative is going to do is make your graph open downward. So if you were to look at maybe the absolute value of a negative x, that would make your graph be the same shape as the red one, but it would be opening downward. So that would be a reflection. So the negative out in front is a reflection of the graph, which is something that we've already talked about in previous sections of these notes, but understand that the negative in this case is a reflection. It has nothing to do on whether the graph is opening larger or skinnier than the parent function graph. Alright, I'm going to invite you to pause the video and draw the 3 graphs that I have on the screen as well. Just so you know, the red graph is the parent function graph. This time it's the square root of x. Oops. The pink graph is the square root of 1/4 x. And the blue graph is the square root of 4x. So again, I invite you to pause the video and draw those 3 graphs. Okay, so taking a look at it, what's happened? Well, all we've done is we've changed the number underneath or inside of the parent function. We've changed it from a 4, a 1, and a 1/4. So we've either made it larger or made it smaller, and see the effect that it has on the graph. So notice that when I make the number smaller, what it does is it appears to make the graph smaller. But really what it's doing is it's making it a horizontal stretch, because it's stretching it out horizontally versus stretching it out vertically. So the pink graph here is a horizontal stretch. And the blue graph, what happens is it appears that the blue graph is bigger, but that's actually known as a horizontal shrink, which can be confusing because what's happening is it's not being spread out as quickly along the horizontal axis here. So this is a horizontal shrink. Okay, so the larger the number is inside of the parent function, the smaller the graph is stretched horizontally. And that's something that you need to keep in mind. Okay, before we actually take a look at the graph, what I want to do is try to apply all of the concepts we've talked about and then verify by going back and looking at the graph. So please don't use the graphing calculator until the very end of this problem. So if I ask you to take a look at the graph of 2 minus 3, or x to the third, and look at the graph of f of 2x, what we want to do is compare what's happening from one graph to the other. So first thing we need to do is find what f of 2x is. So into this equation, what I'm going to do is replace the x with a 2x. So it's going to be 2 minus 2x cubed. So it's 2 minus 8x to the third. So if I'm comparing that to 2 minus x cubed, the only difference that I notice is there's an 8 times the parent function, and then my parent function here is just being times by a 1. So I'm doing 8 times the parent function. So when I multiply the parent function by a number that's greater than 1, then what's going to happen is my graph is going to get stretched vertically. So this should be a vertical stretch. Let's check to see if that actually worked out with the two graphs. Okay, so looking at the graphs now, notice that the blue graph is change color here. The blue graph is 2 minus 8x to the third, and the red graph is 2 minus x to the third. So notice that's what's happening with the blue graph is that it's being stretched vertically. So it's being elongated vertically, which is going to make it appear that it's a much skinnier looking graph because it's being stretched vertically. And that's exactly what happened. So just by understanding the basic idea that this 8 is going to make a vertical stretch because I'm timesing the parent function by 8, lets me know what's happening to my graph. And it was exactly like what we thought the transformation should be.